Very good. And so, anyway, you can kind of introduce yourself, tell about yourself if you care to, and go ahead and talk to us about toroids and calculators and all that stuff. It's all yours, my friend.
All right. Well, thanks for having me back, and I'm happy to be back anytime. This part of my ham radio career, which is now pushing 60 years, is the best part. I certainly enjoyed the time of chasing DX and contests and all that other stuff, but which I don't do much anymore. I haven't fired up the rig in quite a while, but that's all right. I may get the bug again sometime. At least I still have 2 meters to chat to the locals on. Anyway, so as you say, I was licensed, yeah, 55 years ago or something like that, as I can remember, 1965, when I was living in the UK. I'm not a Brit. I'm was born in Los Angeles, so but I lived over in the UK for a number of years, and I still hold a British call sign, M0GCK. Probably never get to use it again, but I am very fond of the UK and have a number of good friends still over there, and often give talks to the clubs over there too, and have lectured a lot by Zoom around the world. Anyway, so let's get on with this presentation tonight here. So I'm going to share my screen, and that should have done it. You're going to share the screen here. I think no, I turned on closed caption, so I clicked on the wrong button. There we go, your entire screen. There we go. All right, share. Okay.
And at the bottom, you see there's a message that says Google is sharing your screen. If you can just click hide on that, otherwise we'll have to see that throughout the whole presentation.
Where's the hide?
Do you see stop sharing at the bottom of your screen? Just to the right of that. There you go.
Oh, there
Perfect.
we are.
Appreciate it.
Okay. Now, where's my desktop? Well, let's go to here. There we are. Good. Got it. We got this. We'll learn it one of these days. Okay, slideshow from the beginning. Okay, I assume you're seeing the introductory title slide?
Looks good.
Good.
Yeah.
Okay. Well, this presentation is definitely for dummies. Whereas this topic, though, has not been for dummies as far as I'm concerned. In fact, it's been a mystery to me for many, many years. I've found the whole issue of toroids and making baluns out of toroids to be a confusing thing, even though I'm university educated in physics and can make my way around equations and charts and graphs and all that stuff. I still found that everything I read about toroids and winding them and so forth to be just a pain in the you know what, and particularly when I got out the books. But I finally think I've made it simple. But most hams, along with Sherlock here, don't have a clue on how to build a ferrite toroid balun. Don't know how to build a toroid, whether it be a 1-to-1, a 4-to-1, a 49-to-1, or a even higher than that. You can build any ratio you want. This is a typical one. That's a 1-to-1 there, typical 1-to-1 balun. And we know about these baluns and we use them. But if somebody said, "Well, how do I make one of those? Where do I get the toroid? What kind of toroid do I get? How many turns of wire do I put on? What kind of wire do I put on it? And all that kind of stuff. This is a big mystery to most hams. Well, it doesn't have to be a mystery because it's really very simple. It's a simple 3-step process that I'm going to show to you tonight. That you don't have to be all confused about. But what most hams do, like this learned gentleman here, is they try to get out the technical books. Now, I've got a whole shelf full of them. I'll show you a picture of them here in a minute. Uh, about technical stuff, including a copy of the 100th edition of the ARRL handbook, which I received a free copy of because I wrote an article in it. In fact, it's in chapter 23 if you want to look it up. It's on 3D printing. But and it has a whole big section on ferrites and so forth in there, and powdered iron toroids and stuff. And I can read it, and it makes some sense to me, but it doesn't really help explain to me how to make a toroid balun. But it doesn't have to be confusing. And these books really haven't been a help to me. And I've read them and read them and read them, and I've collected them just to find out about toroids. And here's my very collection. This is a picture of my bookshelf, which is about 10 feet away from me here. Because there's a tremendous amount of irrelevant, at least for the ham, irrelevant information, powdered iron, ferrite types, and permeability and saturation, and all sorts of stuff like this, and graphs and curves and so forth. You get overwhelmed if you read these books. I did for years. And these are all the big radio Bibles, William Orr's book, and Jasek's and book, and Frederick Terman's book. These are radio Bibles, and of course the ARRL handbook. These are the radio Bibles, and I tried to come to understand how to wind toroid baluns and stuff from these books, and I just found myself confused, basically speaking, until I did a little bit of just simple Einstein-like mind experimenting on toroids and found out it's really pretty simple. It's not a mystery when you begin with basics, when you get back to the primary issues of what a balun does. And because frankly, most hams, if you ask them straight out, what does a balun do? They won't be able to give you a straight answer. They'll give you an answer something like, I guess a balun turns balanced into unbalanced. Well, yes, that's true, but what does that mean? It doesn't mean anything. It's just a bunch of words. That's why I don't like the term balun. Yes, I guess, yes, it is a sort of an acronym for what it does, but that doesn't explain what it does. There's a much better way to explain what it does, and we'll get into that here. What a balun does has to do with skin effect. It very much has to do with skin effect. And to understand baluns, you need to understand skin effect. And I have a whole presentation on skin effect, but let's just quickly review skin effect. Here's a piece of aluminum wire. Why aluminum? Well, most of our antennas are made out of aluminum. It could be copper if you want. And of course, you probably have a copper antenna out on the back of your house, probably a J-pole out there that you made out of copper pipe. But most of our antennas are made out of aluminum. So let's use a piece of aluminum wire. Take a piece of aluminum wire here and cut the end off of it so you can look at the end of it. And if you could look at the current flowing on it, the RF current, radio frequency current, you would find, and you could see it in a different color, it would look like this. You would see that it's all on the surface. It doesn't flow in the middle of the wire at all, or some little bit of it does, but most of it flows right on the surface. It's what we call skin effect. It's caused by the magnetic fields inside of the wire, of the currents flowing inside of the wire, the magnetic field pushes the electric current to the surface. This happens in all conductors. It's called skin effect. We've heard the term, and we basically are familiar with this term. That alternating current, and even at low frequency, even at 60 hertz, this happens. That's why power transmission lines use multiple smaller wires than one big wire for skin effect, improved skin effect loss. And certainly at RF, skin effect is a big, big factor. What this means is, now here's a piece of coax. This is a very important principle. Don't miss this one. Here's a piece of coax cut in half like that piece of wire, consisting of an outer jacket, and I'm not looking at the plastic jacket, I'm looking at the shield. the braid on the outside, and the inner conductor. The blue and the green are the braid, and the red is the inner conductor, whether it's solid or tubular, doesn't matter. But because of skin effect, all of the current that's flowing in the coax migrates its way to the outer surfaces of these conductors. The center conductor only has one outer surface, so all of the current is flowing just on the outside of the center conductor. But on the shield, it has two outer surfaces, the inside of it and the outside of it. Therefore, coax has three surfaces. Therefore, coax is three-conductor transmission line. It's not two-conductor transmission line. If you ran DC down it, it would be two-conductor transmission line. But if you run alternating current down it, or particularly RF down it, it's a three-conductor transmission line, because skin effect breaks the outer shield into two completely separate conductors, the outside of the shield and the inside of the shield. The ones we want of the shield is the inside, the blue one. We don't want the outside. The outside is the bad guy. And that's what the Balun is to get rid of, is to eliminate that third conductor. Here's a cross section of a piece of coax, the same piece of coax we just looked at with the same elements pointed out. Transmitters on the left, and there's a dipole there on the right. The current from the transmitter gets onto the transmission line and comes running up from the transmitter on the blue and the red. Comes running up from the transmitter on the inside of the coax, of the shield, and on the outside of the center conductor by skin effect, and connects to the dipole, where it runs up to the dipole, comes back down the dipole, and then tries to go back down the transmission line to complete the circuit back to the transmitter. But at the end of the coax, which is also connected together where the yellow dots are, also by skin effect connects the ends, the red and the blue and the green together by skin effect. There's a secondary path. There's a connection from the inner to the outer, a short circuit between the inner skin and the outer skin. And the RF current coming back from the dipole now has two ways it can go. It can go back down the blue where it's supposed to go, or it can go back the outside of the shield. And believe me, those two conductors are completely, totally independent. Current can flow on the outside of the shield simultaneously in the opposite direction and in different magnitudes, very, very easily. But how do we prevent that? By putting a choke in the outside shield. The choke can be made of ferrite, or it can be turns in the coax. Either one of them will work. We put a blockage in the shield by putting ferrite around it, or by coiling up the coax. And if we put a blockage that's got an AC resistance of 200 ohms minimum, will sufficiently block off any current running back down the shield. But any place in your antenna system where coax ends, there is that short circuit that connects the inside of the shield to the outside of the shield and creates a third conductor, which is a nasty thing. We don't want it. This is what causes outside shield current. It's what causes that RF that'll bite your lip on your microphone sometimes. It's bad, bad news. Look at this. Here's a nice balanced antenna, open wire fed dipole. Coax, because of the outer shield caused by skin effect, it's just like you went right up to this balanced antenna and hung on a third wire. That's exactly what coax does. It adds a third wire to the outside of the one side of your antenna system. What is that going to do to your antenna system? Do you think the antenna system is going to ignore it? No, it's going to disrupt the antenna system. It likely might change because you don't know where that yellow wire is going to go. It might go to ground. It might go nowhere. You don't know how long it is. You don't know anything about that third wire. It could go all the way back to the power company for all you know. It could. It's an unknown circuit out there. You don't know where in the heck that yellow wire is going to go, and therefore it can disrupt the SWR, can disrupt the tuning, and worst of all, it can disrupt the radiation pattern of your antenna. So you very definitely want to get rid of that outer conductor, outer shield, the outside of the shield of the coax. And remember this, it happens any place coax ends in your system. And that's the place the balun goes, or the thing that I like to call a coax shield choke. So if anybody ever asks you, what's the purpose of a balun? The number one overriding purpose of all baluns, 4-to-1, 9-to-1s, 1-to-1s, coax shield choke. It can also be a transformer, but it always and forever is always a coax outside coax shield choke. All right, that theory aside, but that's an eye opener. That's a very, very important principle. 3 steps now to designing a ferrite toroid balun. By the way, it's also the same 3 steps to designing a ugly balun, a coax balun. We'll mention that later, but we're focusing on ferrite toroid baluns. First of all, get out your cell phone camera, or if I guess you can't record. I guess you can't record here in Google Meet. So get out pencil or pen and paper and write this down, or get out your cell phone camera in your cell phone and take a picture of this slide or write it down. http coil32net online calculators /Amidon ferrite toroid calculator. Or you can get it directly from Amidon if you want to. Go to amidon.com and get the Amidon ferrite toroid calculator. And it's readily available. It's a must-have calculator. It's online. You can get it for free. It's a wonderful little calculator. I have it in a file in my calculators. So get yourself a copy of it. I'm leaving it up here for a few seconds so you can be sure you get a record of it. We're going to use it. And here's what it looks like when you open it up. There's the listing up there at the top. Coil32.net online calculators. You can find it right there just by going to Coil32net online calculators. That calculator needs 3 pieces of information, and that's the 3 pieces of information that are the 3 steps in designing a ferrite balun. You don't need to go to the books to design ferrite baluns. You just need to go to this little calculator, and it'll do all the work for you. You need 3 pieces of information, and you can see them here. The material, the type of toroid, which you'll fill in that little white box at the top arrow. You need the dimension of the toroid. In other words, the size of it, how big the toroid you're going to buy. And we'll show you how to call out the size of the toroid. And the last piece of information you're going to need is how much inductance you want the toroid to have, which is determined by the number of turns that you're going to put on the toroid, which is the output of this calculator. That's what this calculator will do. Once you know the type of the toroid, the mix of the toroid, the size of the toroid, and the inductance you need for it, you push the little blue button and it'll tell you the number of turns to put on the toroid that you just bought from Amidon or that you bought from Ferrite. And you don't need to look at any graphs or any tables or anything else in the technical books. Very simple to build these baluns. Okay, here are the 3 steps. I want to make a record of these too, but here are the 3 steps. First of all, you got to pick a toroid. You got to pick it out for two purposes. You got to pick the mix. You probably heard this term. People swear by mix 31, mix 45, mix 61. You've heard this term mix, pick the mix. Well, we're going to talk about mix here in a minute. You also need to pick the toroid for the size. If you want to run a full gallon or if you just want to run 100 watts, you can pick them different size. Of course, you can use a bigger toroid if you want for a smaller power, but if you only want to run small power, you don't need to pick a big toroid. You can pick a smaller one if you want. They're cheaper, by the way, to pick a smaller one. But if you want to run more power, you want to pick a bigger toroid. But you need to pick a toroid, both for the mix. That's how much the magnetic material is fired into the ceramic toroid. And you need to pick the physical size of it so that it'll handle the power. So you pick the toroid for the mix and for the size. Once you know that, then you need to find out how much inductance do you need on that, in the windings that you put on that toroid. And the amount of inductance that you need is fairly simple. It has to be at least 200 ohms AC resistance. I'll show you how to get that. It's called reactance. It's symbol X sub L. Inductive reactance, it's called. But that's AC resistance. Same resistance, just like common resistance. But it's 200 ohms of AC resistance. And that's created by winding turns on the coil, on the toroid. I'll show you how to do that. That's really quite simple. It's a very simple little formula to work out, which I'm sure all of you can work out. Just simple little algebra equation. Anybody can work it out. I'll even give you a table so you can look it up. Then finally, you'll have enough information with those three pieces of information up there in the top in yellow. Those are the three pieces of information that calculator needs. Then you put them in the calculator, push the button, and voila, you get the number of turns. Wind them on your toroid, and you got a Balun. It's that simple. It's no mystery. Okay, step one, pick a toroid, both for frequency and for power. All right? All right. Here's a little table. You don't need to remember this table or memorize this table. I'm just showing it to you for information. The mix of the toroid is a ratio of the amount of magnetic material that gets fired into the ceramic. Toroids are made out of clay, just like your teacups are. They're a ceramic. They're what we call a ferroceramic. They're just clay fired in a kiln, just like teacups or china plates are, but they have magnetic material mixed in with the clay. So they're what we call ferroceramics. And the mix is how much of the magnetic material and what type of material is put into it. There are two types, but you don't need to worry about the types. You don't need to worry about whether they're powdered iron or whether they're ferrite. Mostly they're ferrite that you're concerned with. And don't trouble yourself with the kind of material it is. Don't read that part of the book. It's irrelevant. There are typically these five different mixes of ferrite that hams ever would use. And frankly, the only three that most hams would ever use are the three in the middle: 61, 43, and 31. And they vary in how magnetic the toroid is, how permeable that's magnetic, how permeable the material, the toroid is. In other words, how magnetic it is. And if you can tell it by just bringing a magnet near the toroid, and you'll see that the 61 toroid is much less magnetic. The 31 toroid is much more magnetic, and the 43 is intermediate. In fact, there's a listing on the right of how magnetic it is. The 61, as you can see, is 125 magnetic. The 43 is 800 magnetic. The 31 is 1500 magnetic. The 73 and the 67 are rarely used by hams, but in case you're making certain more specialty kind of things for very low or very, very high frequencies, you probably would never use a 67 or a 73 mix. The three common toroids that you'll use will be 61 for VHF, 43 and 31 for HF. That's all you'll ever need to know. That's how, and I just show you this chart so that you get a little exposure to what the numbers mean. And you can forget this forever. By the way, if you like a good write-up about this stuff, Karl Leuchtenschwab, good German name, K9LA, has written a very nice paper called "Name That Core," and it'll also tell you how you can identify unknown cores. You got some cores in your junk box, and you wonder what mix they are. And if you've got an MFJ 259B or a similar antenna analyzer, just put a loop of wire through the toroid and do a little measurement with your MFJ 259, and you can determine what the mix is. It's really pretty easy. You can get that little article by Karl Leuchtenschwab, and it's there at archive.org. Details, name that core. It's a great little article. That's where I got that graph. You'll recognize it on the left. Great article. You'll see here, these are curves that come from Amidon, and you don't need to learn these curves. I'm only showing them FYI, just to show you the characteristics of these three common ham mixes. And they're the only three mixes really you need to pay any attention to. You'll notice that the mix 31, which a lot of hams swear by, and you don't need to swear by it. It isn't any better than mix 43, by the way, which is the more common mix for HF. It shows you that they have their peak activity, their peak permeability, which that's what the U means there. The mu there, the Greek letter mu means magnetic ability, and it shows you the range they operate over. You can see their peak activity is between about 3 megahertz and about 30 megahertz. That's HF. These are HF toroids, mix 31. Mix 43 is also an HF toroid, has its peak activity between about 3 and 30 megahertz. Mix 61 has its peak activity in the VHF region. If you wanted to go to a UHF region, you'd probably go to one of those other ones that I showed you on the curve there. But these are the three. So you don't have much of a choice. You don't really need to have much of a choice. It isn't complicated. These are the three toroids you're going to pick. So if you're going to pick a toroid, pick one of these three. I generally use mix 43 toroids. I use mix 31s too. What's the advantage of a mix 31 toroid? Despite the fact a lot of hams absolutely rave about mix 31 toroids, no reason to. There's absolutely no reason to. The only reason you want a mix 31 toroid, notice that it's a little more magnetic. Therefore, you can put fewer turns on it. What's the big deal of that? So you wind a few more turns on the toroid. No big deal. I use mix 43 because they're more common and they're less expensive. Okay, how about the size of the toroid for the power? Oh, the size is determined, the power is determined how big the toroid is. Here's the two common ones, and you really only need to concern yourself with two sizes, the 2.4 inches or the 1.4 inches. And how do you designate them? Toroids are designated by that number up top. FT, ferrite toroid, FT 240, that means 2.4 inches, hyphen 43, that's mix 43. So FT 240 43 is a 2.4 inch mix 43 toroid. Easy, piece of cake. The one on the right is an FT 140. 40, it could be a 43, it could be a 31, it could be a 61, depending upon what band you're going to use it on. There's no difficulty in picking out the toroid. You go to Ferrite and order them, or you go to Amidon and order them. No mystery. You don't have to look through a bunch of complicated books and tables to pick it out. That's all you need to know to pick out a toroid to make a Balun. The size, the mix, and you're away. And the power. Full legal limit will run, one toroid will run full legal limit. If you want to use belt and suspenders, make a stack of two of them and wind the coil on a stack of two of them. And then you have more than enough. Wind the same number of turns. It works just as well with the same number of turns on a stack of two. That way the core will heat up a little bit more, a little bit less. But one is good enough for the legal limit. But two is a little safer. Stack of two you can use. You don't need to do that for 100 watts. If you want to run more than 100 watts, use a bigger toroid. All right, that's step number one. We've picked out our toroid, and it's a piece of cake. Just one of 3 mixes, one of 2 sizes. It's easy. Number 2, find the inductance you need for minimum choking. That's simple, too. Okay, there's a simple little formula. The amount of AC resistance with the symbol X sub L, that's inductive reactance, but that's AC resistance, is simply 2 pi times the frequency you want to operate the Balun at, or anything above. By the way, you can use a Balun at pretty much any frequency higher than you make it for. So if you make a 160 meter Balun, you can run it on 40 meters or 80 meters or 20 meters or 10 meters, and it'll work fine. It'll just work even better. So you make your toroid for the lowest frequency you want to make it for. So if you wanted to make a 160 meter Balun, you just take 200 ohms, which is the minimum amount of choking impedance you need, on the lowest band you want to operate it on. And why 200 ohms? Well, that's 4 times 50 ohms. That's the impedance of your coax, impedance of your antenna system, 50 ohms. You can use more if you want. And that's fine if you want to. That's no problem with it. But 50 ohms is sufficient. Generally accepted standard that 50 ohms is enough. Oh, I know you'll go on the webs and it'll tell you use 1,000 ohms, use 2,000 ohms. That's belt and suspenders. You don't need to do it. 200 ohms is enough. So all we have to do is put 200 ohms equals 2 pi, which is 6.28, times the frequency, 1.8 megahertz if you want to make a 160 meter Balun, times, and it'll give you the inductance. Rearranging, which is easy enough to do if you know a little algebra, the number of microhenries you need is 6.28 times the frequency in megahertz, and if it was 160 meters, it would be 1.8 megahertz. And if you use microhenries and megahertz, they'll cancel out all the numbers. So put in the number of microhenries and the number of megahertz into this little simple formula, 6.28 times the frequency in megahertz divided by 200, and it'll give you the number of microhenries. Almost anybody can work that little equation. So work it out, and it'll give you the number of microhenries you need to put into the calculator. But if you're not even able to work that much math, here's a little table for you. I worked it out for you and put it into a little Excel spreadsheet. And if you want the Excel spreadsheet, get out your camera and take a picture of this slide, and it'll give you the number of microhenries you need. 17.7 for 160 meters, which, by the way, will work for any band higher than that. Or if you don't need to work 160 meters, you can use less, and so forth, down to 10 meters there. If you want to only work 10 meters, then 1.1 microhenry is good enough. And it'll tell you that, and that's the number of microhenries you're going to need. So now we've got the number of microhenries, we've got the size of the toroid, and we've got the mix. We've got the 3 things we need to make ourselves a Balun by using the little simple calculator. So let's do it. Step number 3. Let's turn these into windings. Now, here's the point to remember. If you're making a 1-to-1 Balun, then this will be both windings, both the input and the output of your Balun. If you're making a 4-to-1 Balun, it's all you need to pay attention to is the side hooked to the coax, the one side. You don't need to pay attention to the 4 side, because it'll take care of itself because it's more turns. It's more than enough choking. Or if it's the 9 side, you don't need to pay attention to the 9 side. We only need to pay attention to the 1 side, the smallest number of turns. So the smallest winding is all you need to pay attention to. That's what the calculator will calculate for you. Once you know the smallest side, you just put 4 times as many or 9 times as many on the bigger side. The one connected to the coax is the one you need to pay attention to. So that's the only difference, whether you're winding a 4-to-1 or a 9-to-1 or a 1-to-1. Pay attention to the 1 side. Okay, we now have all 3 that we need for the calculator. So let's build a toroid Balun. a 100 watt mix 43, 160 meter and higher Balun. Let's build the Balun. And there it is. Here's the calculator, the free little calculator from Amazon, obtainable from Coil 43. It's available from them. Mix 43, there it is. We put it into the calculator. We put in the FT140 toroid, which was for 100 watts. If we wanted for a kilowatt, we put in an FT240. Or if we want to use two of them, fine, use two of them. And if we want to go for 160 meters and higher, we put in 16 microhenries. If we want to put in some other, we don't want to go that low, we can put in less. But this is a 100 watt. This is a 100 watt mix 43 FT140 toroid for 160 meters and above. Push the button, voila, 4 turns. That's what we need on the Balun. Simple. You didn't have to go to the books. You didn't have to look at any charts and tables. That's all you had to do, and you got a Balun. And there it is. And by the way, there's the little article in the current issue of On the Air magazine, which if you're an ARRL member, you can go read the issue of the newbie magazine On the Air magazine. And this very Balun is in this article, is in this issue. And you can see it's 4 turns in a little plastic box with some eye bolts in a little plastic box, 1 to hang it up in a tree and 2 to connect your antenna wire to, or connect your beam antenna to, or whatever you want to feed with this. And this is a 1-to-1 Balun. It's a bifilar, a double winding, coming in from an SO239 jack for your Coax, and a couple of wires coming out to your antenna connection. And again, this is a 1-to-1 Balun, so both sides of them are 4 turns. And what wire did I use? I used zip cord. Why zip cord? Zip cord is great because it's almost 50 ohm transmission line, open wire transmission line. Easy, just wound 4 turns of it through the Balun. That little calculator calculated a piece of cake. Here's a 4-to-1 Balun, and you'll notice it's the same thing. It's a 140, it's a FT140 43 Balun, a toroid, and it's got 7-to-1. You notice this one's got 2 turns on the 50 ohm side, and it's got 14 turns on the other side. So it's a 49-to-1 Balun, and you can see it. Notice the crossover. Some people ask why do they cross the turns over there? That's to break up self-resonance in the toroid. It's not terribly necessary, but it's commonly done. So, but only pay attention to the small winding, which is in this case is a looks like 1, 2, yeah. Anyway, that's a 4-to-1 Balun. Pay attention only to the small side, which is the one that hooks to the Coax. So that's how to do it. There are your 3 inputs to the calculator. Pick the toroid. You've only got 3 choices: mix 31 or mix 43 for HF, mix 61 for VHF, and if you want to go all the way up to UHF, you can pick, I think it's mix 67 or something like that. The size, pick a mix 140 for 100 watts, pick a 240 for a kilowatt, or 2 of them if you want. Calculate the inductance with that simple little equation for 200 ohms plus, or use a little more if you want. Then convert the microhenries to turns using the calculator, and you've got yourself a toroid. Is this hard? No, it's not. It's a piece of cake. No more fretting and fussing over building ferrite toroids. They're a piece of cake. So it really is that easy. I'll leave this up on the screen for you in case you didn't get a copy of it for the first time I showed it to you. I'll leave it up here for a few seconds. It's a real piece of cake to build these toroids. Once I finally figured this out, I realized why was I collecting all of those terribly complicated books and trying to read all that stuff about ferrite toroids and about permeability and all of that stuff and about mixes and all of that stuff. Now, if there are other reasons for toroids, but this one is how you make balance with them. Very, 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 very simple. By the
John,
way,
let me interrupt you for just a second.
sure.
Jeff has put the drawing link in the chat. So if you're interested in putting in for the $25 HRO certificate, go to the chat and do it. Thank you.
Okay, fine. By the way, if you want to make an ugly balun, you know what an ugly balun is? That's a balun made with coax. What some of you probably know what an ugly balun is. Instead of using a toroid to make a balun, to make a choke in the outside of the shield, you simply wind turns of coax around some kind of a form, such as PVC pipe. That's typically an ugly balun. Maybe some of you have got an ugly balun. Yeah, there are all sorts of them on the internet, and typically about 18 turns of RG8 wound on a piece of 4-inch PVC pipe makes a great ugly balun. Here's another calculator, very much like the one that I showed you there for toroids, that works exactly the same way for making ugly baluns and uses the same information in required inductance, same number of microhenries, except now instead of putting in the toroid type, you put in the diameter of your form, the diameter of the wire that you use to the coax, the outer shield of the coax that you're winding the ugly balun with, and you can obtain that there from that QR code, or there's the actual URL to go to at Translator Cafe, unit converter, enable US calculator coil inductance. This is for making ugly baluns, but it uses the same identical 3 steps to get yourself to a choke balun in the outside of the coax. And of course, this is only for a 1-to-1 balun. This won't make a 4-to-1 or a 9-to-1, but it's very good if you want to make an ugly balun by just winding a coil of coax in the balun. Or you can make a bundled balun. You know, a lot of hams just use a 4-turn bundle of coax to feed their beam antenna. And this is the way you figure it out, how to do it. Or maybe put it on a piece of PVC pipe, or wind a torus knot by looping the turns back through itself. So you don't need to have zip ties to hold it all together. This is either one of these 2 calculators is wonderful for making baluns. You don't need to do a lot of complicated calculations. So there it is. That's baluns. They're really pretty easy.
Questions for John?
Yeah, I got a quick question.
Sure.
On that last slide, you had the 7-to-1 turns for a 49-to-1 balun. Seems like that would be a 7-to-1 balun.
It's a 7. Baluns are done this way. The 7-to-1 is the turns ratio. The 49-to-1 is the impedance ratio. So a 7-to-1, this is a square. The impedance ratio of the balun is the square of the turns ratio.
Oh, okay. All right.
So a 4-to-1 balun has a 16-to-1 impedance ratio. A 7-to-1 turns ratio balun has a 49-to-1 impedance ratio. So whatever impedance comes in, 49 the impedance out is 49-to-1. That works very, very well. If you make a 9-to-1 balun, you get an 81-to-1 impedance ratio. They
Okay,
work.
great.
They work very well for end-fed half waves. The
Great,
7-to-1 or the 9-to-1s.
Yeah, thank you.
We had a question over on our YouTube. James asking, are these baluns voltage or current baluns, and what's the difference?
They're current baluns. I never use voltage baluns. I hate voltage baluns. They're terrible in the face of high SWR. If you've got an antenna that has a relatively low SWR, then the voltage balance are fine. Unfortunately, an awful lot of antenna tuners, which claim to have balanced outputs in them, use voltage balance to try to fake being balanced tuners. They're not really balanced tuners. And they are often voltage balanced, and they're terrible if you're trying to feed an unbalanced, if you're trying to feed an off-center fed balanced antenna. I don't like voltage balance. I never use them. Current balance to me are the only balance to use. And all of these balance that I'm showing you are current balance, choke balance.
Okay, any other questions? If not, we'll see if we're ready, Jeff, with the drawing. Okay, you got a hand there from somebody at the bottom. Let's see, how do we get that? Okay, I'm not getting to you there. Jeff, can you help me?
I've got 9 entries, and I'll go ahead and spin the.
Okay, we got a question here.
Oh, sorry, that was I was on Moakstein Sparky, I believe.
What was that drawn?
I'm not sure if you can see it, but I'm being the Meet admin, I can see that. But it's a Moakstein.
Yeah.
Morgenstein Sparking.
Yeah, go right ahead, sir.
Yeah, hello to the learning net. My name's
Hello.
Evan Smoke, KF0 FBI,
Love, are you done? Oh,
and I
sorry.
need to probably change my Google title there. I have a question for John.
Okay.
I made a homebrew 6-meter hex beam. That
Okay.
worked very well, but when I made it, it told me to use these clamp-on toroids.
Uh-huh. Split
Yeah,
beads.
that I got from DX Engineering,
Uh-huh. They
And
work well.
and they told me that it told me what numbers I needed to do and how many to use them. Is that a calculatory thing?
I like Snap-on. I like Snap-on split beads, the cubical ones, or sometimes they're kind of rounded on the edge. They work very well. I have a whole box full of mixed 43. You can often buy them surplus quite cheaply, and frankly, snapping a number of them on the coax right below the antenna makes a great Balun, and I just put a bunch of them on. So they work very, very well.
I had no clue why I'm snapping this on the wire.
Well,
And
they're
this
just,
presentation tonight 100% explained it.
yeah.
The
It's-
inner and outer current plane of a
Yeah.
shield.
Yeah, I take a very pragmatic approach to that whenever I'm designing antennas. I just use overkill. I grab my box full of Snap-on mixed HF antenna, for example. I grab my box full of Snap-on mixed 43 split bead toroids, and I snap a whole bunch of them on the transmission line just to be sure I'm not getting anything back down the coax, which is detuning the antenna so that I'm not looking at the coax as part of my antenna. Because I've made some very big mistakes in the past by trying to tune up a new antenna that I don't really know its characteristics because the coax was getting into the action. But putting those Snap-on beads on, and you can't use too many. The more you use, the better it chokes. So don't fear putting them on, and you can put them on both ends. A lot of hams like to put a whole bunch of them right at their shack to be sure that nothing gets out of the shack. I do that too.
No, very good. I learned a lot about that. I'm a dumb retired master electrician, and when it comes to this RF, I might as well throw my code book out the door. So,
Yeah, RF's quite an animal.
all right, great presentation, John, and thanks to the club for putting this on. Okay,
Anytime. I'm enjoying this part of ham radio the best of my career. I've made enough contacts, won enough awards, so forth. But writing articles and helping out hams this way has been the best thing that's ever happened to me. And Zoom to me or net meeting is wonderful. It's just opened up a whole new realm of ham radio for me.
Well, that's for sure. Without this stuff, especially since COVID, we'd be, dead in the water, so to speak. But well, and if there's no other questions, I'm going to have Jeff spin the barrel there and see who we get for a winner.
Okay, and we had 9 entries, and I spun the barrel, and believe it or not, Ron Evans, KF0FPI, aka Moke or Mokenstein Sparky, is our winner. Congratulations, Ron.
Okay, John, we're going to need to make sure we get your correct. Are you correct in QRZ somewhere?
I'm correct to your club. I think I'm due up till July.
Well, that's fine.
I've won this time or two before, but I let the last one expire. So,
Okay.
all good. You should have all my current information.
Okay, so it's Ron Evans. Give me your call, Ron.
That's Kilo Foxtrot 0, Foxtrot Papa, India.
Okay, got it. Thank you very much.
I tuned in almost every one of these for the last year and a half.
Well, great. Glad to have you. Come back next time.
You guys doing it.
Great. Thank you. Okay. Well, good deal. It's just about 8 o'clock, so that ran real well time-wise. And if there's nothing else, anybody got a question or comment? Otherwise, we'll bid you a good evening and thanks for joining us tonight. Jerome, again, thanks for doing the call it the pre-net.
Yep.
Very good. And I'm done. Anybody else? Okay, hearing none. Good night. Good night, everybody. See you next time. Adios.
NBC Television.